Hello everyone. In this second video of our machine learning language prereqs, or jargon you might call, or language, whatever you might want to call it, we are going to look at another 15 sets of definitions, formulas, and terms that we see frequently in machine learning. The last measure we saw in the previous video was entropy, and we learned that entropy is a measure of uncertainty, surprise, or information content, which we define as negative summation over I of pi I log 2 of pi I. Now there is another term called cross entropy. This one is basically a measure of how two distributions are close. Remember, so far we had measures when we talked about distances. We had measures of how close two vectors are, x and y, and how close a point x is to a distribution with a known average and a known covariance matrix, Mahalanobis. Now here we are talking about how close two distributions are together. And if we call those distributions P and Q, so we have these are the probability density functions, P and Q. If we want to see how close they are, then we take a summation over K of what? Negative of Pk natural log of Qk. And you see this is very similar to the entropy definition, except you change the second one from P and change it to Q. Okay, and instead of log 2 we use natural log, but you can still use log 2. Okay, so it all depends on the type of distributions that you have in P and Q. Are they binary, are they multi-class, or so on? But in general, whatever logarithm that you use, you clearly see the definition are very similar. So we call this entropy, but cross entropy, because it measures between P and Q. And you might say, okay, fine, now where would you use this? One of the places that you use this is in logistic regression. Remember, like when we wanted to do a linear regression, the measure that we used for cost function was what? Sum squared error, right? Use sum squared error, mean squared error, or something like that. This was what we used for a logistic regression. Now, for a linear regression, I'm sorry. For logistic regression, when the goal is to identify only between two classes and where we use that sigmoid function, if we want to measure how good the model is, and if we consider our model to be f of xi and w, where xi are the inputs, w are the weights used in the function, and the outputs, the output data are, so here I said the data, I have to say output data. The outputs, or the desired outputs, are yi. Can you provide us a loss function, right, a cost function that I can use to optimize, and that tells me how good my model is, and using that I can get my optimum W's? Yes, that's where we use the cross entropy. And here you see the cross entropy I made is using yi's and then f. Instead of P and Q, I used the empirical, basically, density function using y's, and the one that you get from your model f's. And you clearly see I have used such term here, but not only I have this term, I have a complementary term. And why do I have a complementary term? Because I have two classes in general. It's either yi or 1 minus yi, because yi could either be 0 or 1. Remember, I only have two classes. And if I consider those two classes to be 0 or 1, then one, basically the first part of this cost function is for the first class, the second part is for the second class, and I'm considering the total cross entropy. I also divided by the number of data to do some normalization, and then of course that one has no effect on the final answer for W, and then that is my cost function. So now if I take partial of J with respect to W and set it to 0, that should give me my optimum model weights. Okay, so this cross entropy is used in logistic regression. It's one of the places we use this. What else do we have? One of the methods that we use a lot, most of the time, for optimization of cost functions is called gradient descent, or you might call it standard gradient descent, or some people might even call it vanilla or batch gradient descent. There are so many different names for this, but the standard gradient descent, GD method, I have one video entirely devoted to this topic. If you go under my playlist optimization, you see I explain how this method works. But basically, if I want to put it very simple, this method says whatever cost function I have, if I want to optimize it and get to, let's say, the minimum point, then I first get the gradient of that cost function with respect to the W's. Okay? So partial of J with respect to the entire vector field, this is what? This is a gradient. And if I move in the negative gradient direction, that is the fastest way that I can reduce the value of the function J. It's called the fastest downhill or descent rate, okay? So that's why we call it the gradient descent. Now, if I am at any value for, here, instead of applying it for the whole vector W, I'm showing it that it is done for an individual weight. So it says the individual weight new value is whatever it was, the old value, minus some number times the gradient, but only the component of the gradient related to this W. So this is a vector. This gradient is a vector, right? It's like partial of J with respect to W1, partial of J with respect to W2, and so on and so forth. So now the jth component, which is partial of J with respect to Wj, this one, we use it to update the jth weight. And how much do we move in this negative gradient direction? The amount that we move in that direction is shown by this parameter alpha, which we call the learning rate. There is a typo here. The learning rate. And this learning rate is an important parameter in any gradient descent. Why? Because if I use it so small, it makes my convergence toward the minimum point slow. But it has one good advantage. The advantage is, please watch the video I have over over there, we call it the step size. But that is the step size. So whether we call it step size or learning rate, in machine learning we call it learning rate instead of step size. In terms of optimization, it is a step size. If it is small, the good thing is you don't take the chance of passing an optimum value along the gradient and going basically overshooting and then coming back, and so it reduces the amount of bounces between the basically reliefs of a cost function, right? And although in a sense it makes it slower, but it reduces all of the oscillations, the overshooting. If you make it too big, it makes the convergence in general faster, but you have a good chance of passing over a minimum profile along the gradients and going to some maximum, going over hill, and then coming back. So finding the optimum of that and tuning it is not a trivial task, okay? If the function j is known analytically, you can find an optimum value of alpha in each step. If it's just given based on a bunch of numerical numbers, then you have to tune it. So this is called the gradient descent and the learning rate. Now, when you use this update formula, what kind of data would you pass to this gradient? Look here. So if you look at the gradient, when I want to evaluate the gradients, not only it has the current weights in it, or the previous weights, it has also all of the inputs and the outputs. So basically, I pass all of my training data to the cost function. And I use all of my training data in each step that I'm trying to update any one of the weights. This method of updating is called a batch method, which is allowing your training data, X and Y here, to be used in the optimization process once, all of them once, for the current iteration. There is a different way that you can do the updates, and that is, instead of using all of the data, you only use one or a portion, small portion of the training data in each iteration, not all of the data. And if you do that, that method is called Stochastic Gradient Descent, or SGD. So as you can see here I'm using only one of the data, right? You can see I'm using one X and one Y data at random for updating the weight WJ. I don't need to use all of the data. And there is some advantage to this method. One is, since you are not using all of the data, a portion or just one data, one set of pair of data, it makes the computations a lot less demanding and make your updates faster. And the second thing is, many times, if there are plateaus of the function j, just choosing one random update, one random data for update, not all of the data, not the major, the entire gradient, allows us to jump around the plateau faster, instead of, because in the plateau the gradient is 0. So practically your optimizer will not change the value of any weights, and you come to a stationary point, although you have never reached the global minimum, right? So your cost function looks something like this if you want to plot it, let's say versus X, for example, or X and Y. Here, let's say just X. So it comes to something here, here you have some flat, and then here you have the global minimum. So if you are here, your gradient is 0, and you won't get any update anymore. But if you use the stochastic method, in the stochastic, the gradient that you calculate using one data is not necessarily 0. It allows some small movement to happen, right? And if it does, and if you keep following that small movements, maybe it finally gets you out of that plateau and into the deep valley where you can find your global minimum. So stochastic gradient descent, in many applications it is faster, and I would say in all of them it is faster, and in many applications can help you not being trapped on a plateau or in a local minimum. The other term that we have to use is momentum, that you hear a lot in this gradient descent. Momentum means what? It means when you're updating your weight. So here, if I bring this term to the left side, this first one is at time t, the second one is the previous one, t minus 1. This is the change or the amount of update in the weight. It says the amount of update in the weight is not only just negative alpha times the gradient, it's also plus, so far until this point it is the same as the top one. It also gets a portion of the previous amount of update. If you look at this term is just like the red term, but one iteration behind. So if this is the amount of current update current weight update, right? This guy here is the previous update. It says whatever you want the current update to be, it should come from the negative gradient plus some portion of the previous update. In other words, you are trying to use the memory, the history of the data. Okay, we are using history. And what's good about it, the good thing is, in cases that, again, you might be trapped, you're using the history. Like what? Again, going back to this example, look here. That's okay. Let me use another function. So when I come from here to here, I had some non-zero update. But when I come from here to here, now if I want to just act based on the gradient, as I told you here, that negative gradient term is 0. Okay, so I'm not going to get any update if I only want to go based on the gradient. But if I say, hey, this previous update, this delta W of t minus 1 was non-zero, I bring a portion of that and add it to this, then it makes my new update, delta W of time t, to not be 0. So it forces me to what? To be moving to the next point. In other words, it's just like a rolling ball. When a rolling ball comes down from a height, when it gets to this point here, it definitely has what? It has some velocity. Although on the plateau there is no change in gravity to give it some kinetic energy, but it carries some momentum from the previous motion, and that will what? Will carry this guy forward. Just like the rolling ball, if it comes down to here, it still keeps moving because it has some velocity from the previous motion. And that is called the momentum, and you get it from the previous what? Previous update, and this gain beta here determines the relative weight between your gradient term and your history term. The bigger you use this means the bigger you use the momentum, and the harder it is for you to forget that you had momentum. So that's about these topics. The next topic is convex function and convex set. We say a function is convex if the line connecting any 2 points on this function is always above the function. You see here the purple line, the values of the purple line connecting these points x1 and x2 is above the function. Okay, so that's what we call it a convex. If it was a concave function, then the line connecting the 2 points would be below the actual function, right? So that's the difference between this one, which is convex, and this one that is concave. Another notion of convexity is for sets, for areas in 2D, 3D, or ND, basically space. We said an area or a set is convex if the line connecting any arbitrary 2 points on it is always inside the set. You see here, this set is concave, so the line connecting these 2 points is a portion of it outside the set. Okay, even if you find one such line, any portion of that line is outside the set for connecting 2 points belonging to the set. That set is a concave set. And this is a convex set, or this is convex, the other one is not convex. Okay, so we see these a lot in optimization, especially optimization of convex functions, okay, is much easier than the functions that are not convex. Okay, so we'll see these topics a lot, especially the parts that it comes to optimization. So I wanted to explain that. The other two topics we talk about are bias and variance. So we know the bias and the variance are what? Bias is basically the like the the difference between the average of your data and the desired average of the data. So here you see that the average of the data points, let's say you're doing a shooting, right, on this target board, and here you see this cross here is the average of those blue points, while you should have shot here in the bullseye. So this big difference that you see in the average of the real data and the desired data, that is called a bias. That's a big bias. While here I have a low bias because the center of the red circle and the center of the blue data are almost in the same place. Okay? Now, both of these, the plots on the left, we call them low bias, well, low variance. Why low variance? Because the spread of the data itself is not too much. All of the data are clustered around each other, right? You see the spread of the data is very limited. You are shooting very close to each other, and the center of that shooting could be close to the desired point or could be not, right? So we have low versus high bias, but both of these are low variance. Now, if the data is spread all over the place, now we say that's a high variance, right? And then the data with high variance still can have its center close to the desired center or can have its center off from the desired center, right? So this is kind of like the worst distribution possible, that you have big bias and big variance. It means you did absolutely a bad job. This one here is the best one, low bias and low variance, where you shoot very close and you shoot very close to the target. That's the best one, right? And then these two are kind of somewhere in between. The matter of fact is, in machine learning, you cannot reduce the bias and reduce the variance both at the same time. So you cannot directly go from here to here. Okay, if this is what you have in the beginning, this one, you cannot just reduce bias and variance at the same time. And that is called the bias variance dilemma or problem. What you can do if you reduce the amount of bias, right? If you go from here to what? To here and reduce the bias, you cannot do an amazing job on the variance. Or if you go this way and reduce what? The variance, your bias is not going to be improved so much. So typically you can only go in one of these directions. This direction here is not typically achievable. Okay, so that's what we call the bias variance dilemma. Now, where is the source of bias? Where is the source of variance, right? Where do they come from? They come from what kind of problems in a machine learning system? So we can say roughly that the bias is coming from the underfitting, and variance comes from the overfitting. Okay, but it's not just that. There is a little bit more than that. So the bias comes from, if we want to say, what do you mean? Underfitting means what? It means the model complexity is not as high as it should be. And one of the reasons is your assumptions in the modeling are big time wrong. They are erroneous. You underestimated the complexity of the model. Maybe you just assumed too simple of a model to model everything in the system, right? And so your model cannot get all the relations between your features, your inputs and outputs. Okay, on the other hand, variance is you're overthinking the problem, you're overfitting. You are just being too sensitive to small fluctuations in the training sets. You don't consider those are coming from some random contributions you cannot easily model, and you try to model them as much as you can. So your model will be like those what? Those, here I showed you those higher order polynomials with lots of oscillations. And here, if you do predictions, one prediction comes here, one prediction comes there, one prediction here, one here, and you have data all over the place, which basically boosts up the variance. Okay, so overfitting and underfitting are some common reasons. The next categories are the epoch, batch, static, and dynamic models. So an epoch is basically what? Means the portion of the time or steps in the training during which each sample in your training set had the opportunity to be used at least once in the optimization process, in updating the weights, the parameter models. Okay, so that depends on now how many data do you use, right? If you use the regular, let's say, gradient descent, then you use all of the data in one iteration. So one simple iteration of updating the weights counts as like one epoch. While if you use the stochastic gradient and you only use one of the data for each update, then you need several updates, lots of updates, until each one of those data randomly selected are used at least one time in the update equation. Then you call it one epoch. So you see, epoch does not necessarily mean one update in the weights. No, it depends on how many data you are using. You have to be using all data at least once before you can call it this is one epoch, right? So that's the difference between epoch. Batch, right? Batch is the number of data that you use through the update, which could be all of the data or could be one data at random. Or you might call it a mini batch, where it's just basically a subset of the training data that you're using. Okay, so that's the epoch and the batch. And then static versus dynamic model means what? A static model is the model that you train once offline, and then when you want to use it in some real life applications, you use a model that has already been trained. Before you start your real life application, you already set up, you already trained your model, and now you're using it. And now if during this application, real life application, anything changes, you see some new type of data that you have never seen during the training, then you're not going to retrain the system. You're going to stick to the model that is already trained. That's called a static model. While in dynamic, you try to capture some of these new data and use those in retraining your network and making your network and by when I say network, I mean neural network. It doesn't need to necessarily be neural network. Your machine learning algorithm to be more adaptable to the new set of data. That's what we call a dynamic modeling. Of course, dynamic modeling means you need to have real-time updating. And it means real-time applications. You have to have very fast methods and very good processing power to do a dynamic model. Static model, you do it, you have all the time in the world to do it before you use it in real-life application. So this is offline, that is real-time. And that's the major difference. The next topic is conditional probability and independence. If we have the joint probability of A and B, okay, so this is called the joint probability that A and B happen at the same time, together. If you divide the joint probability of A and B by the probability of B, this is called P of A given B. Okay, so this is called P, we say it P of A given B, or the chance of A happening given that B has already happened. We call it conditional probability of A based on B, or conditioned based on B. Okay, now what's the difference between conditional probability, joint probability, or anything like that? Let me, since I will cover this topic in details later in under my probability playlist, But let me just give you a brief example, and then later you can watch my future. It has not been made yet, that video, but I'm going to make it soon. So let's say here you have a deck of cards, 52 different cards, and you want to pick a card, then pick another one, but you do it without replacement. So what does it mean? It means you first pick a card and then don't return it back to the deck, then pick another one. What is the probability that the second one turn out to be an ace card if the first one was also an ace card? Okay? So here we have to define A and B. What is A? What is B? So A means the second card is an ace. Right? B means the first card is an ace. So now what is the chance of A given B? What can I get from any of these? Well, one of the things I need in this formula is P of B. Can I find P of B directly? Well, what's the chance of you draw a card out of a pack and it's an ace? Well, you have 52 cards and 4 out of 52 are ace, so it's going to be 4 out of 52. Correct? What is P of A given B? Can I find the P of A given B directly? Sure. P of A given B is what? If I want to find it directly, and then I'll find it through the formula for you. But what is P of A given B? You have 52 cards and 4 of them were ace. You picked one, so now you have 51 left, and you took one of the aces away, so now you have 3, and you did not return the card back. It was without replacement. So now you only have 3 out of 51. That's the chance of you drawing a second ace out of 51 cards when one of them was already taken. So P of A given B, you see, I can directly calculate this way. So this is P of A given B. Now, could I get the joint probability directly, P of A and B? Sure. You had 52 cards, you took one ace out, the chance is 4 out of 52, and then immediately after you had 51 cards and you took what? You had the chance of 3 because now you only have 3 left, you didn't do replacement, so now your chance is 3 times 51. And so now if you divide this number by this one, you would definitely get this guy back, which is your P of A given B, right? So you could do it either way. You could calculate this one, you can calculate this and multiply together to get this if you want. Or you could get P of A and B and P of B and divide to get P of A given B, okay? So in this case, you could calculate what? 2 of them and get the third one either way, but it is up to you. It depends on which one is easier for you to calculate. Maybe somebody asks you, what is the chance that A and B are happening at the same time, right? And that's what you do, okay? Now, independence is a situation like this where the probability of one event does not depend on the other thing happening. Basically, the two phenomenon are statistically independent from each other. What does that mean on the formula? It means P of A given B is the same as P of A. It means happening B does not affect happening A, and vice versa. Happening A is not going to affect happening B. So P of B given A is the same as P of A. So A has no effect on B, B has no effect on A. Or you can say P of A and B is the product of the two. Because if you go up here and say, well, this is just the same as P of A, and you cross multiply, you see P of AB is P of B times P of A. So the joint probability is what? The product which you saw in this previous example. Okay, not every two things are necessarily independent. Not always the joint probability is the product of the individual ones. Some phenomena do depend on each other. The happening of the first one will significantly change the chances of the second one. It happens in many things which are sequential, and they affect the future outcomes. One outcome will affect the future outcomes significantly. Now, another thing very closely related to independence and conditional probability is the Bayes theorem. And you use Bayes theorem a lot. If you remember from our previous video, one of our machine learning algorithm was called naive Bayes classifier. So they use the Bayes theorem. What is Bayes theorem? It's directly coming from the definition of this conditional probability. If you look here, P of A given B is P of A and B divided by P of B, and similarly you can say P of B given A is P of A and B again, or B and A, which is the same as A and B, divided by P of A. Well, you know these two are the same, so if you cross multiply, you see that PA times PB given A is the same as PB times P of A given B, right? So if you do that, let me write it for you. You'll get this. And now all you need from here is to find one of these conditional probabilities based on the rest of it. So for example, if I want what? P of A given B from here is going to be PA times P of B given A divided by what? P of B, and that's exactly this guy. So this Bayes theorem directly comes from the definition of conditional probability, and you might say, well, that's just a simple equality. What's the importance of this? Well, the importance comes from how you use this. And one of the places that this one comes in, and you'll see in the next topic, is called maximum a-posteriori estimation. Remember, in the past we had a maximum likelihood estimation, right? That was one of the ways to estimate the model parameters, maximum likelihood. Here, you had a model, you had some observation, and you try to find parameters so that the chance of this observation coming from the model becomes max. We call it maximum likelihood. Now there is something closely related to that called maximum a-posteriori, or MAP estimate, which comes from the Bayes theorem. But before I go and jump into that, I want to talk about this Bayes theorem with one example. Okay, because we use this Bayes theorem a lot, and again, I'm going to cover this topic in one of my future videos on the playlist probabilities, but it's a good idea to look at least one very simple example of this. Like what? So let's see the use of it in machine learning. Let's assume that the word offer occurs in 80% of spam messages or emails, and it occurs in 10% of the desired emails. If 30% of the received emails in general are scam, what is the chance that a new email that you get will contain the word spam? Will contain the word offer is a spam. So let me repeat the question. What is the chance that a new email that you get and it has the word offer in it, it is what? It is a spam. So here we have one thing which is being spam. We have the other thing which is the email contains the word offer. Okay, these are A and B, and how can we formulate it based on the Bayes theorem? So here A is being spam, or image or message, it says. Is a spam, and then B means the message has the word offer, right? So now clearly P of A given B, which is what is the chance of being a spam if it has the word offer, is exactly your question. So this term that I am circling, that term is exactly P of A given B. In order to calculate it, I need what? P of B given A, P of A, and P of B. What does P of B given A means? It means the chance of what? The chance of the email has the word offer and we know it's a spam. So that we know the image is a spam, what's the chance that it has the word offer in it? So let's take a look. What is this guy? And you see here it says the word offer occurs 80% in the spam messages. So that's exactly, if you read it and compare it with the definition of A and B, this is exactly P of B given A. The word offer shows up in spam images for 80%. So that's 0.8 or 80%. What is P of A? It's the general chance of a message being spam. And you see it is what? It is here. It's this guy. We use a different color. Maybe black. So P of A means the chance of something being a spam. It says 30% of the messages are scam. So that's here, 0.3. And then finally what? It says what is the chance of B? What is the chance of emails containing the word offer? It says the word offer occurs in 10% of the emails. So that is 10%. So now what is your chance? You get what? You get 2.4, which is not possible. So you might say, where have I gone wrong? Everything seems fine, but you know probability cannot go more than 1. So what is it that you missed? I'll tell you. This is the part that you missed, the denominator, the normalizing factor is what you missed. So let me clean it up and I tell you what happened here. The answer to P of B is not 0.1. It's a little bit different. So let me show you that one. So here you can say my message is either what? Your message is either a spam or not. Or scam. Here we are using the words scam and spam kind of interchangeably. They are not exactly the same, but anyways, the chance of the message not being a proper real message is what? You see, 30% of the emails, the messages are spam or scam, whatever you want to call it, 0.3. And definitely the other 70% are not. They are real emails, they are real messages. Now, if they are scam emails, then what's the chance that they have the word offer? Based on here, it appears in 80% of them. But if they are not spam emails or messages, now what's the chance that they have the word offer? It says it happens in general in 10% of desired emails. So that's where this 10% is. So now, what is the total chance that you have the word offer? If you want to get the total chance of the word offer, right here, sorry, P of B, right, what should you do? You have to add these together. So here, your total probability is 0.3 times 0.8. Here, it is 0.7 times 0.1. So your total thing, your P of B, is summation of those numbers. So you're not going to just put this 0.1 there. You have to pay attention to the definition of 0.1. 0.1 is the chance that if you have the word offer, but in desired emails. So your P of B is summation of that. And here, I'm going to write it down for you. So now, if you calculate all this, your probability is going to be what? If I calculate it, it will be 0.77 or 774. Okay, so this is the probability that what? That you have the email, the message being spam if it contains the word offer. Okay, so hopefully you can see how I'm using what? The Bayes theorem, right? With a simple example. Now, going back to what does it have to do with the maximum a posteriori estimation? So, when we did maximum likelihood, what did we try to maximize? It was this function. This is what we had. We got some observation. Let's see here. Here. We got some observation, and we had some what? Model parameters. And we tried to maximize the likelihood function by changing my parameters. So the chance of that observation, that data coming from that model is the maximum possible, right? That is called the maximum likelihood. The arg min, actually it should be the arg max, not the arg min, because you're maximizing the probability, not minimizing. You're maximizing the probability of the function f. But what is the maximum a posteriori? What does it add? The only thing that it adds is this guy, g of w. And what is g of w? That's the general probability of that parameter model. So what is it that you need to have extra here? If you have a probability distribution for the model parameter, not only you have to have a model for the observation given the model parameters, you also have to have an extra distribution, which is the distribution for that model parameter. If you have that, which we call prior information or prior function, we know ahead of time what's the chance that such model parameters exist in general without paying attention to the observations or anything. Just focus on that model parameter alone. If you have these two functions, then I try to multiply them together and get the maximum of that W function, and that is called maximum a posteriori. And you might say, well, what does it have to do with the Bayes theorem? So let me show you. Let me first clean this. So if you look here, this function f of x given w, your model given your what? Given your parameter, that one exactly corresponds to this p of b given a. And this other one, g of w, that one exactly corresponds to p of a. And you're trying to maximize the numerator, which is almost the same as this one, except you're neglecting this p of b. Why do you neglect this p of b? What is p of b here? P of b for us is probability of x, probability of the observation, which has nothing to do with my model parameters. Remember, whether it's maximum likelihood or maximum a posteriori, your goal is to find w. Your goal is to find the parameters. You don't care about the frequency of the data showing up. And by the way, whatever it is a constant term, which has nothing to do with your parameter. So since this is a constant term, you're going to neglect it. Because if you're dividing a variable term by a constant term, the optimum point of the variable term in the numerator is going to be the same as whether you divide it also by a constant or not. So because the denominator is a constant with respect to w, it has nothing to do with w, then you neglect the denominator and you only what? Maximize the numerator. That's like you are maximizing the conditional probability. Okay? So what is it that you are really maximizing here? If you go with the definition, this one will maximize what function for me? It will maximize the probability of what? Probability of w given x. This is the function that I'm trying to maximize here. Which is what? If I see some data, I'm trying to maximize the chance that the parameter model is what I think it is. In maximum likelihood, you maximize this one. What parameter can I choose to maximize the chance that the observation comes from the model? Here you are doing the opposite. You say, what? What is the model parameter that maximizes the chance that this model comes from or was the reason for such data? And what's the difference between these two? Right? Because both of them, the first part of them is the same. If you look, the first part of both of these functions is f of x and w, or p of x and w. So what is it that this maximum a posteriori has extra? That's this term only, the prior function. Is that such a good thing to have? Yes. This is an extra piece of information, prior probability of the model parameters. Not always you have such luxury to know the frequency of your model parameters happening in real life. That's not something you always do. But if you do, you're trying to take advantage of it. And what is it in this example? In this example, it's this information here, this guy. That I know that 30% of the received emails are scams. Not always you have such luxury of knowing 30% of the emails I receive in general is scam. How can you get such thing? Well, you have to collect tons and tons of messages and sit down and label them. Hey, this is a spam, this is not. You need a human to label all those. So collecting such a thing, getting this prior function is typically very expensive, time consuming. Not always you have the luxury, but if you do, that helps this estimate to be more relevant, more robust than the maximum likelihood estimate. So if you can get the map estimate, in general, is always preferred over maximum likelihood, but it needs this piece of information that you don't always have access to. Okay, as I said, these two topics are the topics of their own. They need 1 or 2 lectures, maximum likelihood and posteriori, to explain them. So here my goal was really to give you some general information, not really to make you any expert in any of those. The next topic is called Markov process or Markov property, or MP, and then Markov chain. This is another thing that you see in many different applications, including reinforcement learning. So what is it? Markov property also is referred to as no memory property. What does it mean? It means the future of the system, the situation of the system in the future, the state of the system in the future, does only depend on what? The chance that I end up in any situation in the future, it only depends on what? On the current state and the current action. That's all. I do not care about what happens in the past. Here, we do not care about any of these. Your future state, your future situation, repeat it one more time, only depends on what you do at the moment, where you are and what you do. Current state, current action. No dependence on the past. So that's why we call it no memory system. Okay? Not every system is like that. Correct? Some systems show such property, some systems don't. You might say, like what? Let's take a look at an example. Let's say you're driving, and S here means being in which lane, right? Which lane of the road. Well, if you are in the second lane right now, and your action is to turn a little bit to the left, change one lane toward left, which lane would you end up? You're going to be in the third lane from the right, or the first lane from the left, correct? So depending on what you do and what your action is, again, right, this is a 3-lane street. You are right now here, and you decide to go here. So of course you end up here. Now, does that depend on maybe in the past you were here, or you were here before coming to the current position, or you were here? Does it have anything to do with that? No. Where you end up, it depends on where you started, or where you are starting right now, and what action you are taking. If in the past you were in any other lane, it has nothing to do with what you end up. Correct? So it's very clear. On the other hand, if you, instead of defining S to be which lane you are at, you talk S to be like what? Gas mileage, right? MPG, miles per gallon. And your action is how much to push the throttle. And this MPG is MPG average. So now, if you look at the dashboard of your car, which is showing MPG, or maybe it is showing just a number MPG on the dashboard of the car, right? Let's say right now it is showing 29.8. Now, if you apply your throttle a little bit harder, correct? Or a little bit softer, is that going to change this number without looking at how you pushed at this guy in the past? No, of course it does, because what you're defining is an average. So not only how you are pushing the throttle right now is going to affect this number, how you have been driving in the past, it is also going to affect that number. Maybe right now you're doing very amazing, you're doing like a cruise, which brings down this MPG below, bump it up, I'm sorry, make it very high, because that's the best gas mileage is when you are going in cruise, right? You're not accelerating or decelerating suddenly, right? So you might say, oh, look, I'm driving amazingly. I'm not doing too much pushing on the throttle or too much brake or anything. But why is it that still this number is not jumping very high all of a sudden? Well, because maybe in the past 10 minutes or 5 minutes you have been doing a very bad driving. Since that's an average, that's not an instantaneous. If that was an instantaneous MPG, then yes, you will see that number immediately respond to how you are pushing the throttle and brake. But if that was an average, depends on how you define this, then yes, it is not going to be a Markov property. So definitely, it clearly depends on what you're doing with S and N, how you're defining them. Then your system could have a Markov property, which is no history, or it might depend on the previous history. Now, what is Markov chain? Markov chain is a set of transitions from one state to another state with a matrix showing the probability of these transitions. So it says if you are in this state and you want to go to another state, or you are in this state, you want to go to that state, and so on, you have so much of what? Probabilities. And this transition matrix, some of the probabilities in each row will cover all of different things you can potentially do. So some of that is going to be what? 1. It's like, for example, you're playing chess, right? And you are in a special cell right now. Let's say here, and this is, let's say, the king that can move to all of those. So now what's the probability that this guy can go to each and every one of them? So if I call each one of them a state, each one of these cells, and the king is likely to move in each one of them, then you need to have what? You need to have 9 cells or 9 states, and the chance that this king going to each and every one of them is 1/9, because it can go likely to each and every one of them, right? While if it was a pawn, and the pawn can only move forward 1 unit, then the probability that it goes to this cell is what? 1, and the probability that it can go to any of the other cells could or could not be 0. Definitely in the cells I'm showing with orange or red, that's definitely 0. And in these two with, let's say, pink, if there is another piece that the pawn can hit, then you have some chance over there. Otherwise, it can only go straight. So you see now the chance of the transition from the blue to the surrounding ones is not all uniform. You have a bunch of different numbers, right? So you might get something like, for example, hey, there is nothing around, or maybe there is something here. So I have like what? I have 1/2 for there, 1/2 for here. There is nothing there, and there is nothing all around those other ones. Okay? So depending on what you do, but each row shows the chance of you go from one state to all other states. And when you go to the next row, now your center of focus is going to change to another cell and another cell, another state. So we have this guy called the state transition matrix, and as I said, some of the numbers in each row has to be 1 because it's all different transitions you can possibly have. The next two topics are two functions that we use a lot in machine learning. One of them is the sigmoid or S function, which we definitely, if you remember, I told you we use it in logistic regression. We use it in neural networks, in many applications of regression where the neural network's goal is to estimate an underlying function and so on. And the good thing about it is this function is differentiable and is bounded. It only changes between -1 to positive 1 to 0 in this case. And ideally it only has really two values. Although there is a transition in between, but there is one parameter that you can change, and that changes the slope here. So the simple form of the logistic function is what you just see here. 1 over 1 plus e to the negative x. Clearly, when x is positive infinity, this goes to 0, right? So it's going to be 1 over 1. When x is negative infinity, this is going to be positive infinity. 1 over positive infinity is 0. So this guy only goes from 0 to 1. And at 0, it's going to be 1 over 2, which is 1/2. The slope here at 0, you have to take a derivative from this. If you get the derivative at 0, which is this slope, basically, this slope here, how much is it going to be? If you do that, it's a rational function, so it's going to be negative e to the negative x, so it's e to the negative x over 1 e to the negative x squared. And you plug in at 0, you're going to get, this is going to be 2, it's going to be 1 over 4, if I'm not mistaken. Right, so that's the slope, although here in this picture it looks a lot more than 1/4, but that's the slope at 0. Now, can I change that slope? Yes. In many times you can add a gain here or a weight like w and say e to the negative x times w. Then here this w comes into play outside. And so your slope is going to be w over 4. So now if you choose w to be 10 or 50 or 100, that makes this function, instead of being this smooth like this, it makes the transition very fast like that. So now it's literally for big W's, it is going to be quite similar to a step function, which can only have two classes. Okay, so you either have this class data here or this class. And the transition area is going to be a very, very short region because the W you chose is big. There are other functions also. One of them is arctangent of x, which goes from negative pi over 2 to pi over 2. And then we have tangent hyperbolic of x. Okay? Both of these functions show similar behaviors, and there are some other functions too that act like sigmoid functions, but they are kind of S-type functions which go from one value to the other, and they can be used for binary classifications. The next function we are going to talk about is Softmax function. The Softmax function has this interesting property that if you give it a bunch of real numbers coming from vector z, k real numbers, and these real numbers could be positive, they could be negative, they could be 0 or anything like that. They can have decimals or not. Then it converts this vector of k real numbers into a bunch of numbers that all of them are positive. And not only that, some of the numbers from this new vector, if you call this some new vector, I don't know, maybe vector q. This vector q, if you look at some of the elements in q, right? sum of these elements is equal to 1. So it converts a vector with any type of number in it into a new vector where, first of all of the numbers in it are bigger than 0 and they're all less than what? 1. And some of the numbers in this new vector are equal to 1. So we can say this new vector Q is like a what? Like a probability distribution function. And that is amazing, right? It can convert, for example, -1, 2, 4, 6, and 5. It converts them into a bunch of decimals where some of these decimals are 1 and they are all between 0 to 1. So it converts these numbers, as I said, into what? A probability distribution function or something. How does it do it? It raises the Euler number to the power of each and every one of the components in Z and divided by summation of all these exponentials, right? So for example, the first number is going to be what? E to the 5 divided by e to the 5 plus e to the -1 plus e to the 2 plus e to the 4 plus e to the 6, right? And then it does the next one, e to the -1 is divided by the same denominator, and so on and what? So forth, right? So that's the beauty of this function, Softmax function. And where is it useful? One of the places it is useful is in multi-class classification problems. Most of the stuff we have seen so far were binary classification. You have class 1 or class 2. Many times you have more than 2 classes and you want to know which category does your data belong to. That's where the softmax function come into play, and that's exactly our next topic, binary versus multi-class classification. So let's take a look at that and then we'll see how the softmax function can be used. So we know that if you only have 2 classes of data, then you can pass your data to a sigmoid function and see what the output is. Is that like close to 0 or 1? And that can give you whether it's class 1 or class 2. But if you have more than 2 classes, now what? That sigmoid function cannot be used. So there are several ways you can approach it. One is, let me directly jump to C because we just talked about it, is a softmax function. Okay, so what would you do? You basically use a softmax function to give you a probability of your data belonging to different classes, right? So going back to that example of Z's and sigmas and so on, right? Let's say you passed it. Let's talk about the neural networks, because this is what you typically see at the end layer of a neural network, right? So let's say here you have this image, and this image can belong to, let's say, 5 categories, and these categories are robot, let's say boat, a drone, I would say a gun, and maybe, I don't know, a doll or something like that, a squishy doll. So you want to know which toy category that belongs to, and then you pass that image through a convolution or neural networks, and it gives you values of layer over layer over layer. And at the end of the day, you come down to this last hidden layer where the number in each layer only has 1 number in it. So you end up with that Z vector that I mentioned. And these numbers are like, as I said, 6, -1, 2, 3, and 5. Now, with these numbers, how can I decide this toy belongs to which one of those 5 classes I mentioned? So here is a good time to pass it to a softmax function. So if you do the calculations, here I used MATLAB, and the number that you will get will be like .6959, 0.0006, 0.0127, 0.0346, and 0.2560. So what's the good thing about it is if you're really interested in the max, then you can say that's class 1. But the good thing is it doesn't just give you one single one and a bunch of zeros, it gives you a probability distribution. It says 70% chance it is class 1, 25.6% chance it is class 5, almost no chance it is class 2, 1% it is class 3, and 3-4% it is class 4. So it gives you confidence degree in how much chance you have this picture belongs to each class. And that's the good thing about the softmax function. So it gives you a probability list for each classes, not just a bunch of zeros and ones. If you want, now you can pass it through a threshold function or a max function, and that's one of the other things we see, pooling, which I'll show you later, which convert it to zeros and ones. If you are, at the end of the day, you don't want to show probabilities, you want to say, yes, definitely class 1, nothing else, then you can do some processing on this number. But here it gives you the level of confidence or probability of belonging to each class. The other things you can do is, you might say, well, I still want to use the binary classifier and the sigmoid function, but guess what? I have more than 2 classes, so how can I do it? One is this. You do 1 versus 1. So you're not going to attack this picture against all 5 classes at the same time. This is what you do. If you have this picture with 5 classes, right? So as I told you, let's say I have 5 classes, a robot, as I said, let's say a drone, a boat, a plastic gun, and some doll, right? Instead of doing it this way, you do it 2 at a time. You say, hey, is this robot, is this picture a robot or a drone? You do just a binary classifier. You get a number here. It says, I think it is a robot. Then you say, well, is that a drone or a boat? You get some vote here. Is that a robot or a boat? Is that a robot or a gun? Is that a doll or a gun? You choose all different pairs of the classes. So if you have k classes, you will get k times k minus 1 divided by 2, or the selection of 2 out of k objects, C of 2 out of k combinations, and each one of them will give you a number. And then you look at all these numbers, and the class with the maximum number of votes, the maximum number of winning, is going to be your final winner, right? The other way you can do it is 1 versus all. What is that one? Here you do it like this. You don't say, is it a drone or a robot? It's say, is that a drone or not a drone? Or is that a robot or not a robot? Is that a drone or not a drone? So you do 1 or not that one, basically. That's what you do. You put all the other 4 classes into one category, and you do it that way as a binary. And again, you get all of the votes, and again, the one with the maximum vote is the winner. Okay, we have radial basis function, rectified linear unit or ReLU function, and convolution and pooling. So let's cover them. Radial basis function is a function for which the value output of the function for any feature, for any vector, only depends on its magnitude. You might also see it as f of x equal f of absolute value of x. So all you care about is the radial distance of that point to some center, or the distance between that point and the center. That distance is all that matters is in the output of the function. The direction of the distance between x and a has no role in the magnitude of the function. All that matters is the physical distance. You might say, like, what function? And one of the functions I can tell you is a Gaussian function. In a Gaussian function, if you remember, the formula is what? 1 over square root 2 pi sigma squared exponential of negative x minus mu squared divided by 2 sigma squared. If you look here, if x and mu are two vectors, right, then what? Now, of course, if mu is a vector, then you cannot have sigma like that. You have to have the covariance matrix, okay? And it has to come up with the inverse of that. But if you look here, all that matters is what? If you look, it's the magnitude of this vector squared, right? Nothing else matters here. It's just the radial distance squared. Or simpler versions of that, if I want to look into 1D, is what? You can also say, because yeah, here you don't really see if I say they are scalars, then the direction doesn't matter too much. But if I want to introduce another function to you, one of them is called multi-quadratic. What is this? If I have a vector x, then I multiply vector x by magnitude a, take the norm of that, square it, add a 1 to it, and take a square root. Again, here it's just a magnitude term. Or you might bring that guy to the denominator, and 1 is divided by that whole thing instead of square root. We call it inverse quadratic function. That's another thing, right? If this power 2 was not there, then the direction of x would play a big role. But here, the output is really just a scalar, depending on what? The distance that here your x has from point 0, here your x has from mu, or in general a. That's called a radial basis function. And these are one categories of functions that we use in neural networks. In some neural networks, not all of them. So just wanted you to hopefully remember it when we get to neural networks. If I say radial basis function, we mentioned it at some point. The other type of function that we use a lot in neural network is called the ReLU function, which is the same as the ramp function that we had in controls. If your input is less than 0, the output is 0. If the output is bigger than 0, then it is going to be like the function y equal x, okay, the identity function. So if I want to combine these two behaviors into one criterion, that's the way to go. We say the output is the maximum of 0 and input. So of course, when your input is less than 0, the output is 0. When the function is bigger than 0, when the input is bigger than 0, it is the same as the input. So max of 0 and input, if you call it an output function, this is what we call rectified linear function. Why rectified? Because the linear function itself is like this, correct? For negative numbers, it gives you the same negative number. But here, for negative area, you what? You made it straight instead of going down. So this behavior is called rectified linear function or unit. And that's why you call it ReLU. Re for rectified, LU for linear unit. We use this guy also a lot in neural networks, so just wanted you to know about it. Final things are convolution and pooling. Let me talk about pooling first because we just referred to it a little bit before this topic when we talked about the Softmax function. Let me talk very fast about that and then I come back to convolution. So pooling is what you do in neural networks, typically at the end, toward the end, at most of the time at the output layer, to downsample the data. okay, or come up from some probabilities to a bunch of ones and zeros. Okay, but mostly it is really used for downsampling. Like what? So let's say at the last hidden layer, or a layer before the last hidden layer, in a convolution neural network, and you might say, what is convolution? Well, we're going to see in a second. We have an output like this from, let's say, one of the last hidden layers. Then you want to reduce the size of this 4x4 matrix into a 2x2. What would you do? You break down this 4x4 matrix into 4 2x2 blocks. And in each block, you take what? You take the average of the data, or you take the maximum of the data, or the minimum of the data, or anything. And that is a downsampling technique. So pooling is really like here, like downsampling. So what is the maximum of these four numbers? That's 9. What is the maximum of green one? 7. The red one, 6. The yellow ones, 8. So this is what a downsampled version of that, or you can take the average. The average provides smoother data, smoother transition and downsampling compared to max or min, which are not really that nice behaving. Or one of the things you can do is called the median filter. You can take the median of the numbers, okay, which is one of the things you do in image processing, okay, and I'll refer to that when we get to median filter. So this is called the average filter, the max filter, the median filter. This kind of filtering here we use to bring down or downsample the data, okay, and just wanted to introduce that to you. The other topic that we have is called convolution. And convolution is a linear operation between two vectors in general that basically what it can do, it can, depending on how you define the two sides, because one side of, as I said, you have two vectors. One vector is typically your input. The other vector that you have, we call it the kernel of the convolution. Depending on how you define this kernel, the output of this could have any different size. Okay, and the goal of a convolution is to get what? Is to, let's say, for example, in a convolution neural network, is if I pass an image to it, use different types of kernels, as you can see, and from one image I can generate lots of different values. Then I can apply more kernels to those and get more and more basically data, and then I can process those data. And you might say, like what? What kind of kernel? What's the use of whatever that you're doing? Because you're converting one entity into a bunch of entities. So what is it that you're actually doing? Well, for instance, in images, and again, this is going to be one of my future topics, if you want to detect edges, one of the things you can do is to do convolution of the image by a kernel like this. It's a matrix, 3x3 matrix, and you have 1, 1, 1, 0, 0, 0, negative 1, negative 1, negative 1. What this does, and again, please watch my video that I will post soon on edge detection. This one will detect vertical edges. Or if I do it like this, if I convolve my image by something like this, this one will detect horizontal edges, because you see horizontal change in the layers. Here you see vertical. Okay, so depending on what kernel you use, you can detect different features, basically. That's why we say feature map. We detect different features out of the image, different edges, different corners, different this and that. And the good thing is a linear operation that you can do between the two images. You can consider it as a matrix operation. And here, to clarify it for you using formulas, an example, first, if we go over formula, the convolution of two discrete limited signals f and g, and when I say discrete means they are not continuous, they are only a bunch of quantized values, and there are only a few numbers in each one of these vectors f and g, not infinite number. All you need to do when you convolve two sets of data is you flip one of them, and then what? Then you put that filter, that kernel, you might also call it a filter, over the entries of the other vector, and then move it, slide it, and that gives you a convolution. Now, what does that really mean? So here, let's say my vector f is 1, 2, 3, and my vector g is what you can see, -1, 0, 2, and 4. And I say, what's the convolution of f and g here? So it is equal to, as I said, flip f multiply by g dot product, or pixel wise or element wise, and then slide f over. So what does that mean? First thing, flip this guy over. So make it 3, 2, and 1. Then if this guy is -1, 0, 2, and 4, bring this 3, 2, and 1 and start from the left side and slide it to the right side. So first, put it at the very left. So it is going to be like 1, 2, and 3, like this. And then multiply element-wise. Now, what do you mean by multiply element-wise? Well, right now I can only multiply 1 and -1 because they are related to each other. What should I multiply by 2 and 3? There is nothing for 2 and 3 to multiply to. So one thing you have to do here is to pad the first element by a bunch of zeros. Now pay attention, these zeros are different than some actual zero that you had. If you don't like this zero, let me change it to something else, maybe 5, just for the sake of not being confused. So this is 5, let's say, and these two are zeros. So here is extra zeros that we are doing, we call padding. We are padding the vector by enough of zeros, so now I can do it. Now what's the result? If you do element-wise product of the filter by these 3 elements, the result is definitely -1. So the first thing you will get is -1. Then you slide this guy 1 unit to the right. So now what happens? Now you shifted 1 unit to the right. So now you will get 3, 2, and 1 here. Okay, and now again do element-wise product. So it's 5, -2 plus 0, so that's 3. So here we go, I put 3. Slide it 1 more time. So now it should come here. Do the product again, right? And that's 12 minus 3, that's 9. And do a few more of this. So we come here this time. Again, do it. That's 4 and 4, 8 plus 15, that's 23. And we also need to move it all the way to the right until this 3 meets 4. So we need 2 extra zeros here also. We need to pad it on this side as well. So now we can bring it here. And that's 6, and that's 8, that's 14. And finally, move 1 more unit. And this is 12. So this is the result of convolution of this one and this one. Okay, you flip one of them, and you slide it over the other one where it is padded with enough of zeros, you get the convolution version. And this convolution gives you some new data out of what? Out of your original input using some filter. Now, if I use a different filter than F, I would get some different numbers. Okay? And this is what we call convolution. We use it a lot in computer vision and in neural networks dealing with images, which we call, as I told you, we call them convolutional neural networks, those that use convolution in their layers as one of the operations going from one layer to next. And that can give you lots of different features that you can use for classification and regression and so on and so on. It's mostly classifications. Okay, if the dimensions of F is n entries and G is m entries, then convolution of F and G will have n plus m plus 1. As you can see, this is 3 elements, that is 4 elements, and 3n plus m minus 1. I'm sorry, here a typo is n plus m minus 1. So here it's going to be 3 plus 4, that's 7, minus 1, that is going to be what? 6 entries. So n plus m minus 1. Again, sorry for the typo. So here are the next 15 topics that we have covered for you. And I will see you in my next video, where I start focusing on one of the main machine learning algorithms in details, and we are going to implement it in MATLAB and see how it works. Thank you so much. We'll see you in my next video.